Lecture 19 covers section 6.2 through 6.4. At the end of today's lecture, you should be able to formulate the definition of entropy, and you should calculate the entropy of a substance given two independent properties. Lastly, you should be able to calculate the change of entropy for a reversible process. Before we talk about entropy, let us revisit the Clausius inequality. The Clausius inequality indicates that the more negative the cyclic integral of our heat transfer per our boundary temperature, that the more irreversibilities we have within our system. And the Clausius inequality can be stated mathematically as a cyclic integral of delta Q per T evaluated at our boundary temperatures has to be less than or equal to 0. The definition of entropy follows our path independence formulation of work. That is, let us consider a control mass undergoing a reversible cycle between an initial and final state. That is, we have state 1 and state 2, and we can go from state 1 to state 2 via path A or via path B, and we will return from state 2 to state 1 via path C. Let us consider the cycle between states 1 and 2 taking path A and C. The Clausius inequality would be stated as the cyclic integral of delta Q per T would be equal to the integral from state 1 to state 2 of delta Q per T via path A plus the integral from state 2 to state 1 of delta Q per T via path C. Now consider the same control mass undergoing the reversible cycle between states 1 and 2 via B and C. Our Clausius inequality could be expressed as the cyclic integral of delta Q per T would be equal to the integral from state 1 to state 2 of delta Q per T via path B per the integral from state 2 to state 1 of delta Q per T via path C. The cyclic integral from states 1 to 2 via paths A and C and paths B and C are both equal. That is, both of the equations had an identical left-hand side. That is, we can equate the right-hand side of those equations. We'd have the integral from state 1 to state 2 of delta Q per T via path A plus the integral from state 2 to state 1 of delta Q per T via path C being equal to the integral from state 1 to state 2 of delta Q per T via path B plus the integral from state 2 to state 1 of delta Q per T via path C. We notice that we have the same integral, the integral from state 2 to state 1 of delta Q per T via path C on both sides. Therefore, they subtract out. And we see the integral going from state 1 to state 2 of delta Q per T via path A is going to be equal to integral from state 1 to state 2 of delta Q per T via path B. Thus, our cyclic integral, i.e. the quantity of delta Q per T, is the same for all paths between our initial and final state for all reversible processes. That is, once again, we have path independence. We don't care about the path, rather all we care about is our initial and final states. Therefore, we define entropy, denoted by capital S on a per mass basis, lowercase s, which has units of kilojoule per kgK, for a reversible process as ds is equal to delta Q per T. We can define the change of entropy of our system between our initial and final state, i.e. state 1 and state 2, as S2 plus S1 is equal to integral from state 1 to state 2 of delta Q per T. Now entropy is going to be an extensive property, and the change of entropy between two states is the same for all processes. Therefore, our definition is valid for reversible and irreversible processes. Entropy follows the same formulations as did specific volume, specific internal energy, and specific enthalpy. That is, the entropy of our state can be equal to 1 minus our quality times our saturated liquid specific entropy plus our quality times our saturated vapor specific entropy. Or our specific entropy can be equal to our saturated liquid specific entropy plus our quality times our saturated vapor minus our saturated liquid specific entropy. And we see these values published in our steam tables. Entropy is taken in reference to a specified temperatures. For instance, our steam tables set our specific entropy to 0 kilojoule per kgK at a temperature of 0.01 degrees centigrade. However, when we use EES, they sometimes have a different reference temperature. That does not matter, for all we're concerned about is the difference of entropy between our two states. Consider the change of entropy within the Carnot cycle. We can say the cyclic integral of delta Q per T of a reversible cycle is equal to 1 per TH times the integral from state 1 to state 2 of delta Q plus 1 per TL, the integral from state 3 to state 4 of delta Q. Notice how our temperatures move outside our integrals, because for a Carnot cycle we have isothermal heat addition and isothermal heat rejection. This can be stated as Q going from state 1 to state 2 per TH plus Q going from state 3 to state 4 per TL. This would be equal to our entropy at state 2 less that at state 1 plus our entropy at state 4 plus that at state 3. Now we're going to depict this on the TS diagram to see why the Carnot cycle is the most efficient cycle. If we construct a TS diagram, we have the following. As we go from state 1 to state 2, we have an isothermal heat addition process. That is, we are adding heat under a constant temperature. From state 2 to state 3, we have an adiabatic reversible expansion process. That is, it is isentropic. Our entropy is not changing. From state 3 to state 4, we have an isothermal heat rejection process occurring at a low temperature. And then from state 4 to state 1, we have an adiabatic reversible compression process, i.e. our entropy is the same. We note that our increase of entropy going from state 1 to state 2 is equal to our decrease of entropy going from state 3 to state 4. Thus, for a Carnot cycle, our net change of entropy is equal to 0. Additionally, our heat supplied is the area under our curve from going from 1 to 2. That is, QH can be visualized as the red shaded region between the line going from state 1 to state 2. Our heat rejected, QL, is the dashed region beneath the line going from state 3 to state 4. And our work is our difference of our heats. That is, our work is the area enclosed by the box going from state 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Lastly, for an internally reversible process, we can consider the change from saturated liquid to saturated vapor in terms of our entropy. If we have a process where we're going from state 1 to state 2, i.e. in an isothermal process, our change of entropy, S2 less S1, would be 1 per our mass times our temperature times the integral from state 1 to state 2 of delta Q. Or this would be Q going from state 1 to state 2 per T, which, although this process is isothermal, is also isobaric, and our heat supplied going from state 1 to state 2 is our saturated vapor specific enthalpy less our saturated liquid specific enthalpy, and per our temperature. Thus we can say our change of entropy for an isothermal process, S2 less S1, will be equal to H sub G minus H sub F per T. And if we wanted to determine how much heat is transferred going from state 2 to state 3, i.e. once we leave the vapor dome, Q 2 to 3 is equal to 1 per mass times the integral from state 2 to state 3 of delta Q. If we recall from our Clausius inequality, ds is equal to delta Q per T, or delta Q is equal to T ds. Therefore, Q going from state 2 to state 3 would be the integral from state 2 to 3 of T ds. And if we had a functional description of our temperature as a function of entropy, we could solve for this.